would take a near miracle for there not to be life on Mars. Mars and Earth have been swapping spit for billions of years, so anytime either planet is hit by comets or asteroids, some material gets ejected into space, with a tiny fraction of that material eventually landing on the other planet. If any of Earth's microbes happen to have been hitchhiking on that ejected material, then you've got the potential for life on Mars. Plus, we know that Mars in the past wasn't the dry, arid world it is today. Water once flowed on Mars back before it lost its atmosphere to space. And despite all of that, we somehow still don't have any direct evidence for life on Mars. Or do we? Because 50 years ago this month, one of the experiments on board NASA's Viking lander on Mars that was specifically designed to search for signs of life returned a positive result. It's just that all the other experiments on Viking searching for life returned a negative result. And the next few years saw arguments go back and forth in scientific research papers between whether these results could be explained by just chemistry or whether you needed biology, whether you needed life to explain them. Essentially, all asking the same question. Is there life on Mars? So in this video, we're going to dive into all of these details. We'll chat about the Viking landers and what possible evidence they found for life on Mars back in the 1970s, why those results were so controversial, and then finally what evidence we found for life on Mars in the past 50 years since Viking. Like, for example, the fact that Curiosity rover detected origin of life molecules on Mars earlier this year. But if you're seeing a headline like this online that has anything to do with alien life, right? Like, how do you know that it's legit? Well, thanks to Ground News, the sponsor of this week's video that I've been working with for a few years now. I can immediately see that this is a news story covered by 116 sources from around the world, and that 93% of those sources have a high factuality rating. So immediately I know that this is a story I can trust. You all know that here on my channel, I try to make astrophysics accessible for you all and approachable by breaking down complex topics. And that's exactly what Ground News does with the news. They have data-driven tools that make understanding and staying informed with the news just as approachable. And I really like how you can compare the coverage across a story with Ground News. So for example, this Curiosity story, US Today went with the headline, NASA's Curiosity finds never before seen organic molecules on Mars. Whereas Reuters went with NASA rover adds to the list of organic compounds detected on Mars. And Sky News went with Mars rover discovers organic molecules, hinting at possibility of ancient life. So you get the full context of a story this way, accessing all of these diverse perspectives in one place, which their bias comparison feature summarizes really nicely. I use their blind spot feed the most because I also find it so interesting to see which stories have been disproportionately covered by one side of the political spectrum. I've heard from so many of you that you love Ground News as well, so if you head to the link in the description down below or scan the QR code on the screen, you'll save 40% on their Vantage plan to get unlimited access to all of their features, which comes out at around about $5 a month. Those subscriptions help keep Ground News ad-free and so free of any bias that comes with paid advertising. So a huge thanks to Ground News again for sponsoring this video. And now let's dive in and chat all about the Viking controversy and whether we've had evidence for life on Mars for 50 years, and start with, what were the Viking landers? Viking 1 was NASA's first mission to land on Mars, touching down on the 20th of July 1976, almost 50 years to the day when this video gets posted. It was one of two missions sent to study Mars, Viking 1 and 2, both of which had a spacecraft in orbit around Mars and sent down a lander to the surface in 1976. So the spacecraft took images of the surface of Mars from orbit, like for example the famous face on Mars image of a hill that just happens to look a bit like a human face. And of course the landers took images of their surroundings on the surface, including a 300-degree panorama showing off the spacecraft themselves, but also the rock-strewn rolling hills of Mars. One of my favourite facts about the Viking landers is that the onboard computers that would, receive commands from the ground control team on Earth to actually run the lander only had a memory of 6,000 words. And I just think it's a wonderful reminder of how much of the early space exploration was done with such minimal computing power. Now, along with the camera, both landers also had a couple of scientific instruments on board, including weather sensors like a thermometer and a wind anemometer, but also a seismometer to detect Mars quakes, and also some spectrometers to work out what samples of the atmosphere and soil were made of. And then they had 3 experiments specifically designed to search for life. First, the gas exchange experiment, or GEX. So this experiment checked to see if there were any microbes in the Martian soil that were releasing gases as part of their existence, breathing essentially, for want of a better word. So they'd collect a sample of Martian soil and they would add in some water and some nutrients and then put it in a sealed box and then monitor it to see if any common gases associated with life, so whether that might be oxygen, carbon dioxide, methane, nitrogen, see how those levels changed over time and if there were any microbes in the Martian soil that were changing those levels. Then there was the pyrolytic release experiment. So this experiment searched for any microbes that might be in the Martian soil that would make food from sunlight, the way that plants do through photosynthesis. So what they did this time was mix in a bunch of radioactive carbon into a sample of Martian soil. Radioactive so that they could track how much radioactivity there was and see if some carbon was disappearing because it was being used in the photosynthesis process by microbes in the soil. Then there was the labeled release experiment. So this experiment looked for microbes that actually eat food to survive in the same way that humans do. So what they did was added a big nutrient soup to some Martian soil, again along with some radioactive carbon, and then if there were any microbes in the soil that were taking in that radioactive nutrient soup to survive, then they would then breathe out some radioactive carbon gas and then the sensors would pick that up and we'd know that there were microbes in the soil. So then what did the results of these experiments show? Did Viking find evidence for life on Mars in the 1970s? So in 1976, the same year that the Viking landers touched down, is when we had the first research paper published detailing the preliminary results of these experiments. It was written by Klein and collaborators, and then in the following years, more in-depth research papers were published on each of the individual experiments. So let's go through each of the experiments and see what they found, starting with the first on the list there, the gas exchange experiment. So that was the one that was monitoring the levels of different gases that we associate with life in a sample of Martian soil that has been exposed to water and also a bunch of nutrients that life would need. And Klein and collaborators in 1976 reported that a big burst of oxygen was observed after adding the water, H2O, before even the nutrients were added. But it turns out that this big burst of oxygen after adding water is exactly what you'd expect from something known as superoxides. That is what the research paper from Oyama and Badal in 1977 concludes, the one that gave more detail about this specific experiment. They said it was reactive salt, like for example of potassium or calcium or sodium, like a sodium peroxide, that we know react vigorously with water and release a load of oxygen gas that are what are responsible for the results of the experiment. But then what about the carbon dioxide they also saw forming over time in the experiment? Well, that's explained by gamma iron oxide, essentially a really reactive form of rust that when it reacted with the nutrients that were added to the Martian soil produced a load of carbon dioxide over time. So the results from the gas exchange experiment are about as clear-cut of a negative result that you can get in science, with Oyama and Badal stating that all the gas changes observed can most easily be explained or demonstrated by plausible chemical reactions that require no biological processes. So definitely no evidence for life. But what about one of the other experiments? What about the pyrolytic release experiment? The one testing for photosynthesis happening by mixing in a load of radioactive carbon to test how much of it was being pulled out of the air by microbes in Martian soil using it to photosynthesize. Well, in the preliminary results, again reported by Klein and collaborators in 1976, a small amount of that radioactive carbon did disappear. And what's more is when they exposed the Martian soil to extreme heat first, it actually reduced the effect. It reduced the the amount of carbon that was pulled from the air, which is really promising because extreme heat should kill off any life in soil, but shouldn't really affect any chemistry that's going on. But the research paper with the full results was published by Horowitz, Hobby and Hubbard in 1977, and that promising result disappeared. Because when they first heated the Martian soil sample at 90 degrees Celsius for 2 hours, the results didn't change. The same amount of radioactive carbon disappeared from the air. Even heating the soil at 175 degrees Celsius for 3 hours only reduced the effect by about 90%. And that's the big problem, at least for life on Earth as we know it anyway. That shouldn't be able to survive those extreme temperatures. Plus, if you think about it, like the Martian surface never gets above freezing. So any life on Mars should have evolved to cope with extreme cold temperatures and not extreme boiling temperatures. So Horowitz, Hobby and Hubbard's conclusion was that given how heat resistant the reaction was, it's unlikely the reaction is biological. So finally, what about that labeled release experiment? That again used that radioactive carbon tracing trick to work out if there were any microbes that were eating nutrients in the Martian soil. And in the preliminary results reported by Klein and collaborators, there was a positive result with a big release of radioactive gas after the nutrient was added, which then started to level off. And like with the first gas exchange experiment, when they heated the soil sample up to 170 degrees, there was no radioactive gas then given off. The effect disappeared. But when the full experiment results were published later that year by Levin and Stratt in 1976, those results didn't change. In fact, they found the same behaviour from both Martian soil samples, one taken by Viking 1 in one location on Mars and the other by Viking 2 at a different location on Mars. The only thing that changed is that the destruction by heat wasn't as clear-cut as it first seemed. So the radioactive response survived temperatures up to 18 degrees Celsius fully intact, was significantly reduced with really odd cyclical readings after 3 hours at 50 degrees Celsius, and then was finally fully wiped out entirely at 160 degrees Celsius. So Levin and Stratt tried to then recreate what they had seen in a lab here on Earth using like analog soil samples, what we think Mars soil was made of, and then also soil samples from both the Earth and from the moon collected by the Apollo missions. The Earth soil produced a 10 times stronger radioactive carbon signal compared to the Martian soil, but the sample from the moon had a 10 times lower response, similar to a soil sample from Antarctica here on Earth, which has very little life present in it. Which all seems very promising for the idea of life in this Martian soil producing this signal that we're seeing. But on the other hand, the experiment with the Martian soil never gives you the accelerating, exponential growth pattern you'd expect from multiplying microbes, even when left running for over 50 days. So with an explanation of life not seeming to fit, Levin and Stratt then tried to figure out, okay, well, is there a chemical explanation for what we've seen? And after extensive lab work trying to recreate the results that they'd gotten with the Martian soil with, a mixture of other different compounds, like the superoxides, for example, before the peroxides, or even just, the UV exposure of the Martian soil because of the fact that it is in direct sunlight with a very thin atmosphere, they still could not recreate what had been seen with the Martian soil. So unlike the other two experiments, the labeled release experiment was never actually pinned down on a specific chemical reaction. And so the paper from Levin and Stratt ends with the line, "Thus, despite all hypotheses to the contrary, the distinct possibility remains that biological activity has been observed on Mars." Which brings me to part 3, why these results were so controversial. Because at the heart of everything here, all we've got is a release of some radioactive carbon gas from a sample of Martian soil. We've not got, here's an actual Martian microbe. And yes, this release of radioactive gas could be explained by life, but it's probably more likely going to be explained by unknown to us chemistry. And it is worth stating though that this result is still unexplained 50 years later. Now, of course, at the time, this result was very exciting to many, to scientists, to the general public. There was a lot of media coverage around it, and a lot of media coverage around the first preliminary results experiment, and not always so much about the negative results that came after it. But what's key here is that this result from the labeled release experiment doesn't stand alone. So you have to interpret it knowing that the other two biology experiments didn't find evidence for life, and knowing that one of the other instruments on board Viking, one of the mass spectrometers, GCMS, also didn't find evidence for life. GCMS heated the Martian soil samples to try and split out what the soil was made of, what the ingredients were. And specifically, it was hunting for organic molecules, you know, the building blocks for life that mostly contain carbon that cells and proteins need. You'd expect to find these around something living or something that used to be alive. And Klein and collaborators reported that no organic compounds larger than methanol and propane were detected in the Viking 1 soil samples by GCMS. So although the results of the labeled release experiment remain unexplained, we don't have any evidence for life on Mars. But technically, we don't have any evidence that life can't survive on Mars either. And the authors of the original paper to report on the labeled release experiment results, Levin and Strack, continued to publish work stating that biology, aka life, should still be considered as an explanation for the results found by Viking. This was released as recently as 2016. And that's all in part due to the results from the generations of rovers and landers that have come in the 50 years since Viking 1 and 2. Which brings me to the final part of this video. Have we found any evidence for life on Mars since Viking? No. Not directly, sadly. But we have found evidence to suggest that Mars is more hospitable to life as we know it anyway than we originally first thought. So everything from Pathfinder to Curiosity to the Mars Reconnaissance Orbiter have all found evidence for water on Mars. Either abundant liquid water on ancient Mars thanks to the dried up riverbeds that we see, or the ripples on the bottom of ancient lake beds, or the fact that you have subsurface ice on Mars as well. Curiosity also measured seasonal methane in the Martian atmosphere as well. It rises and falls with the seasons in a pattern still not fully explained. Methane tends to be associated with life here on Earth, but again, there's lots of different chemical reactions that could be to blame here. And of course, there are many missions that have now found that organic molecules are present on Mars, which, if you remember, was one of the big results from one of the other experiments on board Viking, the GCMS, that was used in context to conclude that the labeled release experiment also wasn't life. Curiosity found chlorinated hydrocarbons back in 2013. Then in 2018 found larger, more complex organic molecules preserved in a 3 billion-year-old rock. And most recently in 2024, NASA's Perseverance rover found iron phosphates and iron sulfides tangled with organic carbon in a way that on Earth is sometimes produced by microbial activity. Although again, generic chemistry can also do this. Still, that result is now classified by NASA as a genuine potential sign of life rather than just a sign of organics alone. And the result with the most impact that gave new context to the results that Viking found 50 years ago is that the Phoenix lander found super reactive salts in the soil called perchlorates, which is a potential energy source for any microbial activity. But we also know that heating soil with perchlorates in it destroys any organic molecules present in that soil. And that's what they did in the GCMS experiment on Viking. They heated the soil samples to separate out the ingredients. So Viking may accidentally have burned up the very evidence that it was searching for. So now, with the context of the past 50 years worth of results on Mars, do we start looking at the results of Levin and Stratt in a different light? One that favours biology as an explanation more than chemistry. Because in the 50 years since Viking, no lander or rover has carried an instrument to redo the experiment of Levin and Stratt, the labelled release experiment. Instead, NASA and ESA's focus until recently had been to bring Martian samples back to Earth for testing. So instead of doing biological experiments on Mars itself, where the results can be a little bit unreliable and you can't change the plan once you found something that you weren't expecting, you do the test in a research lab with well-tested, reliable, known equipment where you can easily do follow-up tests and repeat experiments for scientific reliability. So Perseverance has been collecting those samples and leaving them on the surface for for a future mission to collect and return to Earth. But the funding for that mission was completely cut in the recent NASA funding cuts announced by the current administration. So sadly, it doesn't look like we're going to get any answers to these questions anytime soon. And there's also the very distinct possibility that by sending more rovers and landers to Mars over the past 50 years, we've been, swapping spit with Mars even more, and we might have already contaminated the surface with Earth microbes. A possibility that only gets more certain if we send humans to Mars in the future. So, as Levin and Stratt pointed out in 2016, the Viking samples are the only data we will ever have on biologically pristine Martian samples. Which might mean that the question that we're all asking in the future won't be, is there life on Mars? But instead will be, before humans got there, was there life on Mars? Either planet is hit by comets or asteroids. Asteroids? Ugh. My hair is really annoying me. I did something different and it just wasn't touching my neck like 5 minutes ago, and now it is, and I'm like, ugh. I mean, I'm trying. This tiny claw clip is like the little claw clip that could, it's just so small for so much hair. Just because there was a bird that flew right over the skylight, it may have changed the light. Don't think it would have cast a shadow on my face, but it might have just made you go for whatever reason. That's what that was. It was a technical term.